All right, we have started. Okay, this is a video with the PowerPoint equilibrium part. I got a little creative there. Part 2. So 2 goals for this one is using the equilibrium values, either in pressure or concentration, to calculate Kp or Kc respectively, and to determine if a reaction is at equilibrium or not equilibrium. So let's go ahead and get started. So how do we calculate the K value if we're given the equilibrium values? Basically, step 1, set up the K expression. So this is the products over reactants, no solids, no liquids. Any coefficient becomes an exponent. So that's the first thing, set up the K expression. So we're going to start there. So if we have this phosphorus pentachloride gas, and it decomposes to phosphorus trichloride gas and chlorine gas, it's a decomposition reaction. So we're given this. Let's set up the K expression, and let's see. It's asking for Kc, so I'm going to set up with the brackets. Ooh, that is a diatomic gas. Don't want to forget. So the brackets mean concentration. Okay, so should be pretty comfortable setting up the K expressions. All right, so that's my first step. The next thing I do is I look at the information that is given. Let me get a different color. Let's get an orange. Okay, this is going to look like a 1970s kitchen with army green and dark orange, but we're just going to go with it. Okay, so at equilibrium, we're given these values. I'm going to draw them on the overhead in a way that I think is easier to organize than just a list. So here's what I would do. I'm going to write the concentration at equilibrium that is given next to the compound. It is 4. Okay, so at equilibrium, the concentration of phosphorus pentachloride is 4.2 times 10 to the minus 5 molar. For phosphorus trichloride, it's 1.3 times 10 to the minus 2 molar. And for chlorine, it's 3.9 times 10 to the minus 3 molar. And the question is, what is Kc? What is the numerical value, to be more specific? So the K expression tells us how the different reactants and products relate to each other mathematically to get a value of K. In order to get the numerical value, I just plug in the equilibrium concentration, and if there's an exponent there, then I would use that exponent just like any other math equation. So it's kind of like if you're given an algebraic expression. X plus 5 equals question mark. Well, I don't know what question mark is unless I know what X is. So this is kind of like us being given those unknown values so that we can calculate K. All right, so when we punch all of that into our calculator, we actually get, I think it's 1.27, I believe. Yes. Okay, I think that's correct. I wrote it down. Double check to make sure. All we're doing is multiplying. Might be off by a decimal place here. 3.9 times 10 to the minus 3 times 1.3 times 10 to the minus 2. All of that is on the numerator, denominator divided by 4.2 times 10 to the minus 5. Okay, I think it's 1.27. I might be off by a decimal place there. Okay, so that's how we get the number k, the value of k. We, number 1, set up the k expression, and 2, plug in the values for, in this case, concentration at equilibrium. But if we wanted the Kp, we would plug in the equilibrium pressures, and we would get Kp. So pretty straightforward, not too bad. All right, we're going to do another example. All right, next slide is this reaction at equilibrium. So this problem, this specific example, has 2 steps. So the first step is we're going to calculate the Kp given the equilibrium pressures and a balanced reaction. So another example of what we just did. And then the second part is new. If we have different numbers, can we tell if it's at equilibrium? And the answer is yes. Yes, we can. Because math. Okay. All right, I'm going to pick a different green because that is way too 1970s kitchen. Not that I was alive way back then, but you know. Okay. Just kidding, I was. All right, so we have our balanced reaction. Okay, and the first thing I want to do is set up the K expression, and it's giving me pressure and asking for Kp. So I'm going to write the partial pressure of the product ammonia squared is the numerator. Denominator is the partial pressure of hydrogen cubed times the partial pressure of nitrogen, and that one is just an understood 1 because the coefficient in the reaction is an understood 1. Okay, so that's my first step. My second step is going to be plug in the numbers. Okay, and that's what I'm given in that problem. For ammonia, it's 3.1 times 10 to the minus 2 atmospheres. Now that is squared, so I do square that value. For hydrogen, it's 3.1 times 10 to the minus 3 atmospheres. That one is cubed times, I'm multiplying these terms together on the denominator. The partial pressure of nitrogen is 0.85 atmosphere, and that's just to the first power or understood 1. Okay, so let me move this to the other screen, and I'm going to pull up my scientific calculator. All right, so on the top, I've got 3.1 times 10 to the, that's E or EE on your calculator, minus 2, and let's square that, okay, divided by, I'm going to use parentheses, 0.85 times 3.1 times 10 to the minus 3, and that is cubed. Oh, that's a big one. So about 3.8 times 10 to the 4th is what I get. 3.8. So Kp at this temperature is 3.8 times 10 to the 4th. And Kp and Kc are what we call unitless. Okay, so that's the first part of the problem. Given the equilibrium values of pressure and a balanced chemical reaction, calculate the value of Kp. All right, our next part of this problem, this would definitely be 2 separate problems on your exam. Now that we've calculated the Kp, now we're going to use that in the next step. Is it at equilibrium? Does this represent a system at equilibrium? So what we're going to do is determine 3.8 times 10 to the 4th. That didn't look like a superscript on my writing. Let me make that clear. It's 10 to the 4th, 3.8 times 10 to the 4th. That is the value. That is the number of this ratio at equilibrium. So if it's not equal to that, it's not at equilibrium. So I'm just going to put an equal sign with a question mark over it. Question mark over it. Okay. So instead of plugging in those values that I was given in the first part of the problem, now I'm going to plug in the values given in the second. So this part of the question says 0.0167, and that will be squared because it's ammonia in the numerator. On the bottom, we have 0.525 for nitrogen times, for hydrogen, 0.00761, and that is cubed. So we're going to compute this and then ask the question, does it equal that value? If not, it's not at equilibrium. That's all we're doing. Is it at equilibrium? Well, does it equal the number? If yes, yeah, it's at equilibrium. If not, no. All right, 0.0167 squared divided by, parentheses, 0.525 times 0.00761, and that one is cubed. Oh, this is not equal. This is, the number I get is 1205, which is not 1,205, which is not 3.8 times 10 to the fourth. So that's all we do. If it's not at equilibrium, if it's not equal to Kp, or in some cases Kc, then it's not at equilibrium. It's that simple. It's that simple. If you plug in the numbers and you get the value of K, whether it's Kp or Kc, if you're plugging in the pressures and you don't get Kp, it's not at equilibrium. If you plug in the concentration and you don't get that numerical value of Kc, it's not at equilibrium. That's it. That's all we can determine at this point, is whether it's at equilibrium or not. Now moving forward in a little bit, the question I will ask is which way does it need to shift? And that's where we'll look at what we call Q, which is K at any time, sort of this amount. So this would be what we call Q. Q is quotient for reaction. Excuse me, reaction quotient is what Q stands for. K is only at equilibrium. K is only at equilibrium. Q is this ratio set up in that equilibrium constant expression. Q is the value at any time. Anytime we call it Q, the only time we say that number is K is when it's at equilibrium. All right, that one was not too long. Have fun.